All right, today we're going to take a look at analysis of motion acceleration. For this, I'm going to actually show you a video of us physics teachers. We went outside last week and we dropped one of those big green exercise balls. In fact, I have it here. One of these green balls from the press box in what we call free fall, which we'll be talking about next unit. Free fall, letting something fall freely, no strings attached. So I'm going to share that screen with you, and we're going to watch. It's a very quick video. So here it is. That's me at the very top of the press box holding on to one of those green balls way up there. And all the other physics teachers are down here taking a video with the iPads, and we chose what we thought would be the best video. So it's very quick. You'll see me count down, and it doesn't take long for the ball to fall. Mere second and a half, and it's down.
4, 3, 2, 1.
And that's the lap. Hold on a second. Let me get out of there.
Writing's not that easy.
Sorry. YouTube's just going on. All right, so that was lab. Is that quick? So you'll notice with this lab, and I'll share my screen again, we're looking at every 1/10 of a second. So let me share my doc cam with you now. It happens very quickly. So we're going every 1/10 of a second. And normally we would collectively measure this in class. We have little apps on our iPads that can help us measure distance and time. So as physics teachers just went along and did that with you. So normally we would measure this together in class and then work on the lab. And just like that last one on constant velocity, this would normally be something we would do in class, and us teachers would go around our classrooms and help you guys out. But since this is part of our asynchronous, we're gonna share this video with you so to help you do the video. So we have our time values. We're going every 1/10 of a second because it only took about 1.5 seconds to fall. The total height of the press box it's like 30 feet or so. It's about 4.9 meters, which is about 16 feet. So the first second got us probably about halfway down, and that had enough data points for us to make some graphs. And again, we don't do a ton of graphs, but graphing motion is actually an important skill. Since this is acceleration, we cannot use the constant velocity formula. That's only for constant velocity. When something free falls, it gets faster and faster. It actually accelerates. So we have to use one of the 4 acceleration equations. And equation 2 is going to be pretty helpful for us with this. So equation 2, and you'll get to know these equations as the year goes on, is delta x, the distance, equals 1/2 of v1 plus v2 times delta t. It kind of says that distance equals the average velocity times the time. Now for this, v1 is 0 because when it first starts and I let go of it, it isn't quite moving yet. So really this comes out to be delta x equals 1/2 of v2 times delta t, because v1 is simply 0. And here we're solving for the velocity, that last column. So I want to rearrange this equation to solve for v2. Rearranging equations can be a little bit tricky, but it's amazing as the year goes on how great students get at it. In fact, usually when we take the semester exam in January, students will look back at their early work and go, I can't believe I struggled rearranging that equation. It's so easy to me now. So if you struggle a little bit early on, no worries, you're going to get much better at it. So solving for v2, I'm going to multiply both sides by 2. That's the same as dividing by 1/2. So I got 2 delta x equals v2 times delta t. Then to solve for v2, I'm going to divide both sides by delta t. So I got 2 delta x over delta t equals v2. We're solving for the final velocity after 1/10 of a second, the final velocity after 2/10 of a second, final velocity after 3/10 of a second, etc. So our working equation Once we've rearranged equation 2 is simply the velocity is 2 times the distance divided by the time. So now going to the data table and grabbing my calculator, the velocity after 0.1 seconds, I'm going to take 2 times the distance, which is 0.05, divided by the time, 0.1. And I get, oops, hold on, sorry about that, 0.2 times 0.05 divided by 0.1. And I get 1. 1 meter per second. So after a tenth of a second is going 1 meter per second, covering 1 meter in 1 second. After 2/10 of a second, I'm going to take 2 times the distance, so 2 times 0.21 divided by the time of 0.2, and I get 2.1 meters per second. Almost twice as fast as a tenth of a second earlier. After 3/10 of a second, 2 times 0.43 divided by 0.3. I get 2.9 meters per second. I've got 2 times 0.76, 2 times the distance, divided by the time of 0.4, 3.8 meters per second. Notice our velocity is not staying constant. It is changing. It's getting faster and faster, hence the name acceleration. All right, here we go. 2 times 1.23 divided by 0.5, 4.92. So I'm just going to go 4.9. So I'm going to do them now for the remainder. Same thing. So 2 times 1.8 divided by 0.6. Oops, sorry. 2 times 1.8 divided by 0.6. I get 6 meters per second. 2 times 2.4 divided by 0.7, 6.9 meters per second. 2 times 3.16 divided by 0.8, 7.9 meters per second. 2 times 4.01 divided by 0.9, 8.9 meters per second. And finally, 2 times 4.9 divided by 1 is 9.8 meters per second. And again, that got us about half or 2/3 of the way down on that free fall video. And we thought that was enough data points to get to where we want to get to. You know, the final velocity probably would have been 12, 13, 14 meters per second. But again, the velocity is certainly not constant. It's getting faster and faster and faster. And again, we use the equation to rearrange for the velocity, using that as distance, that as time to solve for all those variables. So now we're going to graph, just like we did last time, the position versus time. So my time, as almost always in physics, is going to go on the horizontal axis. We measure that in seconds. My position or distance, which we measure in meters, is going to go on the vertical axis because the distance depends on the time. A timer is an independent variable. It just rolls along. Nothing you can do about it. I want to get up to 1 second. So it actually is going to work where I'm going to go every tenth of a second. So 0.1 second, 0.2, 0.3, 0.4. You get the hang of it. All the way up to 1.0 seconds. Distance-wise, I need to get up to 5. So if I went 1, 2, 3, 4, 5, so I can go 0.5 meters, 1 meter, 1.5 meters, 2 meters, 2.5 meters, 3 meters, 3.5, 4, 4.5, and 5. And there we have our lab titled labeled time and distance and unitized meters and seconds. And I'm doing a good job of using as much of that graph paper as possible. Just good graphing technique.